Hello everyone, I'm Takao Murakami at AIST. Today, I'd like to talk about a location synthesizer called privacy-preserving multiple tensor factorization. First, I briefly explain the outline of this work. Nowadays, a large amount of location traces are collected into an LBS provider, and they can be used for various types of geodata analysis. For example, we can calculate a time-dependent population distribution from traces. It can be used for finding popular POIs, such as popular restaurants at lunchtime. Another example is a transition matrix. A transition matrix is composed of a transition probability from some location to another location. So it can be used for modeling human movement patterns, such as mall to restaurant. The third example is a visit fraction distribution. For each POI, we can calculate a frequency distribution of the visit fraction. And this distribution can be used for annotation of POIs. For example, in this figure, POI A is an office and POI B is a park. We know that many people spend much time at office. For example, they may spend 20% to 60% of their time at office. So we can automatically add an office tag to POI A based on this distribution. So traces are very useful for various geodata analysis, but they may include some sensitive locations such as hospitals and home. To address the privacy issue, the location synthesizer has been widely studied. In this approach, we train a generative model from real traces. Then we generate synthetic traces from the generative model. Ideally, synthetic traces should preserve various statistical features while protecting user privacy. In particular, locations form some clusters, such as those who commute by car and those who often go shopping. And a feature specific to such clusters is important for some geodata analysis tasks. For example, annotation of office POIs requires traces of office workers. So POI annotation requires such cluster-specific features. The cluster-specific feature is also important for generating realistic location datasets. So location synthesizers should have this feature. However, most of the existing location synthesizers do not preserve a cluster-specific feature because they generate traces based on parameters common to all users. So they are not satisfactory in terms of utility. One exception is SGLT, Synthetic Location Traces Generator. This is a state-of-the-art location synthesizer, but it's not scalable because the running time is quadratic in n, the number of users, and cubic in m, the number of locations. So in this work, we propose a new location synthesizer called PPMTF to achieve high utility and scalability. More specifically, our proposal, PPMTF, has the following features. First, it preserves various statistical features such as population distribution and transition metrics. It also preserves cluster-specific features, so it preserves a visit fraction distribution. Second, PPMTF is very scalable. The running time is linear in users and quadratic in locations. For example, when the number of users is 200,000 and the number of locations is 1,000, SGLT would require over 4,000 years to train the generative model. In contrast, PPMTF requires only 2 days, which is 1 million times faster than SGLT. Finally, PPMTF uses plausible deniability as a privacy metric in the same way as SCLT to prevent the inference of real traces from synthetic traces. So we advance the state of the art in terms of utility and scalability at the same level of privacy. But one limitation is that we assume a generative model is kept secret and we protect privacy for only synthetic traces. So providing strong privacy guarantees such as differential privacy for the generative model is left for future work. Okay, so next I will explain more about our proposal. I begin with its overview. First, to preserve transition matrices, we calculate a transition count tensor, which is composed of user, location, and next location. This tensor includes a transition matrix for each user, so it preserves the information about movement patterns. And second, to preserve time-dependent population distributions, we calculate a visit count tensor. This is composed of user, location, and time slot, and includes a visit count for each user, location, and time slot. So this tensor preserves the information about time-dependent population distributions. And to preserve cluster-specific features, we factorize two tensors simultaneously. This is known as multiple tensor factorization. Tensor factorization is a kind of clustering. So a generative model preserves the information about clusters, such as those who commute by car and those who go shopping. And finally, to generate synthetic traces, we reconstruct tensors from a generative model, and we generate traces from the reconstructed tensor via the MH algorithm. Okay, this is a high-level overview. And now I explain the details. First, we calculate two tensors from training traces. The first tensor is a transition count tensor, which is a transition count matrix for each user. In this example, user U1 has one transition from X2 to X3. So the corresponding element is 1. The second tensor is a visit count tensor, which is a visit count vector for each user and time slot. And in this example, user U1 visits X2 and X3 in time slot 1. So the corresponding elements are 1. Then we factorize two tensors simultaneously. Here, A, B, C, and D are called factor matrices, and each column in A, B, C, and D represents a cluster. For example, in this figure, the first column in B, C, and D has high values at birth, and night, respectively. Then the first column in A represents a cluster of users who go to birth at night. So there are Z clusters in this example, and the clusters are automatically found from training traces. Finally, we generate traces from reconstructed tensors. For each user UN and time slot T, we calculate a visit probability vector PNT from the second tensor. Then, from the first tensor, we calculate a transition matrix QNT whose stationary vector is PNT via the MH algorithm. And finally, we generate locations for each user and time slot using the corresponding stationary vector and transition matrix. Okay, this is our proposal. And next, I will explain how to protect privacy in our proposal. As I explained, PPMTF generates a synthetic trace Y for user UN using a generative model. And we use plausible deniability as a privacy metric. Formally, KYPD satisfies this inequality for input user UN and K-1 other users UM. So the linkage of UN and Y is alleviated by PD. And we can calculate this probability. So we release a synthetic trace Y only when it provides KYPD. And we can explain the overall privacy of PPMTF based on PD. We generate a synthetic trace Y for user UN using AN, B, C, and D, where AN is the nth row of A. And AN is a user profile of UN. And now the linkage of UN and Y is alleviated by PD. So the leakage of AN is also alleviated by PD. And B and C are information about locations, which is called location profile. And D is information about time, which is called time profile. So the leakage of information about users is alleviated by KYPD. And we also empirically show the privacy of PPMTF. So now I explain our experiments. In our experiments, we first used the SNS-based people flow dataset in Tokyo. Here, we set each time interval and time slot to 20 minutes. And we extracted traces from 9 a.m. to 7 p.m. for 500 training users and 500 testing users. And for privacy, we consider the re-identification attack. Here, we use the Bayesian re-identification algorithm to re-identify input user UN from each synthetic trace Y. For utility, we calculated a time-dependent population distribution for testing traces and synthetic traces, and then we evaluated the average total variation between the two distributions. We call this TP-TV. And here we have the results. SCD is a synthetic data generator, and SCD and SCLT are two existing location synthesizers. And C in SCLT is a parameter that represents the number of clusters. And we set C to various values. And we can see that SCD and SCLT result in high re-identification rate. This is because they generate synthetic traces by copying some training locations. In contrast, PPMTF achieves low re-identification rate while keeping high utility, which is close to training traces. We also showed that PPMTF preserves transition matrices, so for more details, please see our paper. And to evaluate the privacy more, we also considered the membership inference attack. Here, we used a likelihood ratio-based MI algorithm to determine for each 1,000 users whether she is a training user or not. So we determined whether each user is a member or non-member. And here we have the results. The membership advantage is the difference between the true possible rate and false possible rate. So lower is better. And we can see that PPMTF achieves low membership advantage while keeping high utility. We consider this is because the inequality in PD holds for both training and testing users in practice. We also visualized some columns in factor matrices B and C and training traces and synthetic traces whose values in A are high. The green line is Shinjuku line and the orange line is Fukushima line. So we can see that PPMTF preserves cluster-specific features, such as those who commute by train, and we generate synthetic traces based on the cluster-specific features. Next, we evaluated the scalability, and here we have the results. SCLT is exactly cubic in M, the number of locations, and quadratic in N, the number of users. In contrast, PPMTF is quadratic in M and linear in N. So, for example, when N is 200,000 and M is 1,000, SCLT would require over 4,000 years, and PPMTF requires only 2 days. Finally, we used a 4-square dataset in New York, and we evaluated the visit fraction distribution. Here, we evaluated the PPMTF with 10, 1 PD and SCD. We didn't evaluate SCLT because it cannot be applied to this large dataset. And we can see that in SCD, all users spend almost the same amount of time on each POI. This is because SCD uses parameters common to all users. So SCD cannot preserve the visit fraction distribution. In contrast, PPMTF preserves the cluster-specific features such as office workers, so it preserves the visit fraction distribution. And the annotation of POIs such as park and office is possible. Okay, let me summarize this talk. We proposed PPMTF, which preserves various statistical features, including clustering cluster-specific features. It's also scalable, and we can handle 1 million users. For future work, we'd like to provide strong privacy guarantees, such as differential privacy for a generative model. For example, differential privacy with small epsilon might be achieved by releasing only B, C, and D, and randomly generating A. So we'd like to investigate how much epsilon can be reduced by this approach. Okay, that's all, and thank you for your attention.